Hello, my name is Ashley Barker, and for the next couple of minutes I will be explaining how to determine Qgas. In order to find Qgas, I will be using the equilibrium constant method. It's based on the Gibbs free energy method, but does not require any software that I don't already have. We've said in class that we hit equilibrium when we hit the minimum of the Gibbs free energy function, and I've broken down the method for finding Qgas into 3 steps: getting Kp, stoichiometry, and the equilibrium constant equations. The goal is to get Kp as a function of temperature in order to ultimately get composition versus temperature. The first step in the code is to get Kp as a function of temperature for water splitting and for carbon dioxide splitting using the data from table A28 in the textbook. Be sure to calculate the real Kp value from the natural log of Kp given in the table. You will also need to include the interpolation equation in order to pull Kp values for temperatures not explicitly given in the table. The second step is to calculate the mole fractions. A sample of the code for finding X for one temperature is shown on the right. Using stoichiometry, you can determine Y and Z. For the third step, you have to utilize the equilibrium constant equations. And to generate the plot requested by Kerensky, you have to find the mole fractions for the reactants and products for a range of temperatures using the Kp function I mentioned earlier, which makes for a really fun MATLAB code. The results plot shows that the water splitting with the solid lines and the carbon dioxide splitting with the dashed lines on a mole fraction versus temperature plot. This graph makes sense intuitively because the mole fraction should add up to 1 at all times. So as the water or carbon dioxide on the left-hand side of the equation decreases, the hydrogen and oxygen or carbon monoxide and oxygen products increase. It's also important to note that there are more products in the higher temperatures and we want more products, which means that our solar input has to heat up this water or this carbon dioxide more in order to get more products. This accomplishes our goal of determining the composition, which is something we need in order to calculate, using the enthalpy functions, what the enthalpy entering and leaving the reactor is. One last note, you can tell we don't make much hydrogen or carbon monoxide through this process, which means it's pretty inefficient and far from ideal. Alright, so I hope you learned the process of determining Qgas from this presentation.